And we're back, folks. So this is section 3.1, chapter 3. Let's go. We're in chapter 3. This is when I get to talk to you guys all about, like, okay, remember all the difficult stuff we did in chapter 2? There's shortcuts to all that stuff. Now, the shortcuts themselves are kind of difficult as well. You know, we only talked about derivatives of very minute topics. Like, we didn't discuss derivatives of trigonometry at all. We didn't really discuss the derivatives of exponential or the derivatives of logarithmic functions, you know? So in this chapter, by the end of chapter 3, you should be able to know how to find the derivative of anything. Of anything that I could throw at you. By the end of chapter 3, by Christmas time, you should be able to find the derivative of anything. Okay? So what we're going to focus on today is derivatives of polynomials and exponentials. Okay, that's this section. Finding the derivatives of polynomials and exponentials. Now, thinking back to how we were finding the derivative before. Okay, on yesterday's test, the only way that we would know how to find the derivative is to run it through the f of x plus h minus f of x all over h and let the limit of h go to 0, right? Some sort of algebraic way to reduce it down to get h out of the denominator and then plug in h, right? What we're going to do now is take piece by piece each type of different function and see if there's a pattern that we can create. You know, I kind of already did this for you guys on the very last section with some power rules, some polynomial ones. So we kind of have talked about it just a little bit. We just basically scratched the surface of it. But again, what we're going to do from here on out is take each different type of function, find the derivative, the old-fashioned way, and then see if there's a way that we can create a rule for it. So let's start very basic. Let's start with the most basic type of function we can get, just a constant function. What happens if we try to find the limit as h goes to 0 of f of x plus h minus f of x all over h, just a constant, just a number, okay? X equal, or y equals 3, something like that, right? Okay, well then the derivative would be, here's our formal derivative, right? F of x plus h. Well, if f of x is just a number, so like f of x is equal to c, right? Just equal to a constant, like 4 or 3 or whatever. Well, the function, no matter what I put in, is just c. So f of x plus h is just c. And f of x is just c, just the constant, right? So we end up getting this c minus c over h. Well, c minus c is 0. 0 over h is 0. And the limit as h goes to 0 of 0 is not undefined. Remember, the limit of a constant, which 0 is just a constant, the limit of the constant is the constant. So the limit as h goes to 0 of 0 ends up being 0. So what I'm saying here is that the derivative of any constant, f prime of x, when f of x is any constant, is always 0. I used an arbitrary value there, right? I could have used 3, but that would have been a little bit too specific. I could have used 5, that would have been a little bit too specific. So what we're saying here is if f of x is equal to c, some constant, the derivative is always equal to 0, okay? Now, I'm going to be giving these to you in Leibniz notation because it's a little bit easier to write that way, okay? So I introduced it a little bit in the second chapter, but we're going to be using it a lot more in the third chapter. This Leibniz notation where I have d over dx of. Because the reason I'm saying this is because it's harder to write in that prime notation, okay? Remember, d over dx just means the operation of the derivative. If I apply the derivative on c, just the constant, if I apply the derivative on c, it's equal to 0, okay? If I wanted to write this out in our old way, I would have had to say this. This whole statement could be written like this in Leibniz notation. If f of x is c, then f prime of x is 0. That whole statement can be written just as d over dx of c is equal to 0, okay? The operation of the derivative on c is 0. Okay? That's really saying if f of x is equal to c, then f prime of x is equal to 0. F prime of that function. See, we can't use this prime notation. It's not like I can say f prime of c is equal to 0. No, that doesn't make sense because the function is the constant. The function is the constant. It's not like what I'm putting into the derivative, okay? So now we have a rule for just constants. If you ever want to find the derivative of a constant, it's always 0. Now, why is that the case? Well, we saw it algebraically, but think of any function that's constant. Isn't that the graph of any constant function, just a horizontal line? What's the slope of that? Does it ever change? No. So the derivative must always be 0, right? It must also be the constant, just 0. We're going to do that here each time we find the derivative. Okay, we next look at the functions f of x is equal to x to the n. The power functions. F of x is equal to x to the n. So this is going to include x to the first, x to the second, x to the third, just plain old x, and also negative exponents as well. We'll get to by the end of today. Okay, so if n is 1, that just means I'm going to find the f of x is equal to x. Y is equal to x. Okay, if I wanted to graph y is equal to x, let's kind of picture it in our brains. That's just our diagonal line running through the first and third quadrants, right? What's the slope of that line? 1. Does it ever change? No. So that must mean the derivative of x, just f of x is equal to x, the derivative of y equals x must always be 1, right? Must always be 1. Could I have verified it using my f of x plus h minus f of x all over h equation? Of course we could have. But I don't need to here because I can visually see that the slope is always going to be 1. So I can say d over dx is just x. Okay, if the function is just y equals x, then d over dx of x is just 1. Okay, d over dx of just x is 1. So let's keep going with the powers. Okay, let's keep going with the powers. It might be a very good idea for you guys, because I see some people not doing this, to start making yourself lists of common derivatives, like the derivative of constant, like we talked about last slide, the derivative of just x equals 1. Okay, let's pump up the power a little bit. What about x squared? Well, we saw in our last chapter that x squared was going to end up being 2x. We've already seen these cases in our notes, way back last chapter. They say in section 2.8, exercises 19 and 20. I guess we did it. I don't remember. But we have seen that d over dx of x squared is 2x, and d over dx of x to the third is 3x squared. What kind of pattern do you notice there? What happened to the power? Goes to the front. And then the exponent decreases by a value of 1. Does that pattern happen here as well? X to the third goes in front. 3 goes in front. Decrease the power by 1. 3x squared. For n equals 4, we find the derivative. You know, I'm just showing you that this is what it would look like using the definition of a derivative. The f of x plus h minus f of x all over h. Look at all this hard work that you can just say is, what do you think is going to happen to x to the fourth? 4 get brought out front, knock the power down by 1. What? Why am I showing you all of this work? Because if I asked you to do this problem on yesterday's test, you would have had to do it that way, right? F of x plus h minus f of x all over h. Algebraically reduce it all down, get the h out of the denominator, plug in at h going to 0, and then see what would happen. But guess what? Now, because we're smarter, and we've learned it, we can say that the power is going to come out front, and I can decrease the exponent by a factor of 1, by a unit of 1, okay? So how do we state that? Well, this is called the power rule. the power rule. D over dx of x to the n power. So this is any power on x. X to the fourth, x to the fifth, x to the millionth. You bring the exponent in front, it gets multiplied, and then you decrease the power by 1. You bring the exponent down front, and you decrease the power by 1. This is an extremely powerful, it's funny, it's called the power rule. This is an extremely important, useful rule that we're going to use all the time. Right now, we're talking about it only as positive integers, but honestly, this works for negative integers as well. Okay, so again, the rule is bring the power in front, decrease it by 1. Power in front, decrease by 1. So let's do that a little bit. If f of x is equal to x to the 6th power, think about the work that you're saving yourself. Like, think about this. If I truly wanted to find f prime of x, that would be x plus h to the 6th power minus f of x all over h. I would have to work all of that out. But you know what it ends up being? 6x to the 5th. Whoa, holy cow. That's it. If I were to truly factor or FOIL all of this out, all the way to the 6th power, subtract this, reduce that all by a factor of h, it would just all reduce to 6x to the 5th. Ooh, man, that's awesome. Okay, let's take a look at b, x to 1,000. I can't even imagine how much time that would take. 1,000, sorry, that's an x. Yikes. 1,000 x to the 999. Now, look at this new notation that you're given here in C. dy dt. Okay, dy dt. All that is saying is take the equation y, find the derivative with respect to t. Okay? Look at the equation that I'm given. Y equals, okay, that makes sense. The derivative with respect to the function y using variable t. Oh, okay, t to the 4th. That's all that's saying, and really it's just 4t to the 3rd. And again, this is using Leibniz notation, the d over dr. D over dr, d over dx, same thing, just telling you what variable they're using. So d over dr of r to the 3rd, 3r squared. And again, please appreciate the amount of work that this rule is saving you. Like, you would have to be taking all of these things to those powers. Yikes. Man, that's so easy. Just to bring it down in front, reduce the power by 1. Okay? Okay, so that's for positive integers, right? So what happens if it's a negative integer? Let's take a look at it. What about power functions with negative integer exponents? Okay. Take a look at, looks like we did this in a problem in the book or something. In exercise 65, we ask you to verify from the definition of a derivative that d over dx of 1 over x is negative 1 over x squared. We can rewrite that as negative 1 over x to the negative 2nd power. Take a look here. Does the rule still apply? If I have d over dx of x to the negative 1st, did I really bring the negative 1 out in front and decrease the power by 1? Yes. So even negative exponents will work the exact same way. So if we even have negative exponents, you still do the exact same thing. Okay? If I have d over dx of x to the negative 1st, it's negative 1 times x to the, don't forget, decreasing a power. I know this is silly to say, but decreasing a negative power will go more into the negative direction. Okay? So like if I have an x to the negative 1st power, the power is going to end up being x to the negative 2nd. Now, Don't forget that negative exponents, like I would really like us to write it like that in the end. Negative exponents will always turn into fractions as well. Okay? So, that being said, the derivative of negative exponents ends up being fractions. Okay? Getting more and more complicated fractions. You know, we will also see that it holds for all negative integers. Let's take a look at fractions now. What if the exponent is a fraction? Do you guys remember what fractional exponents are? They're roots, right? What do you think about x to the 1/2 power? Isn't that the square root of x? X to the 1/2 power is the square root of x. It actually is still written 1/2. Look, bring it out front, 1/2 x. And then think about taking 1/2 minus 1. 1/2 minus 1. What do you get? Negative 1/2. That's still the same rule that we're using. Okay? No matter if the power is negative, no matter if the power is rational, fractional, whatever, you do the exact same thing. Now, we will reduce that. So that's like saying 1/2 times 1 over the square root of x. We actually did that in chapter 2. We did this in chapter 2. But we did it the long way. We did it the way where you have to multiply numerator and denominator by the conjugate. Remember that? We did that problem. But now we can reduce that work to all just saying, okay, it's 1 over 2 radical x. Okay? So this is the general version of the power rule, but guess what? It's the exact same thing as what you wrote down before. What we're saying here is now you can apply that power rule to any sort of power. If n is any real number, rational, irrational, positive, negative, doesn't matter. The power rule still exists. The power rule still applies. Kick it down front, bring down by a factor of 1. So let's differentiate here. If f of x is equal to 1 over x squared, here's what I say. If it's ever an exponent and something weird is happening to it, like it's in a radical or it's in a denominator, try to make it just the power on x. Like for example here, isn't f of x x to the negative second power here? Isn't 1 over x squared x to the negative second power? I'm kind of like unsimplifying it a little bit. Because technically I should write it as 1 over x squared. You know, we learned back in algebra that you should never leave negative exponents, but I'll tell you what, it's easier to differentiate with negative exponents. Okay, so that means that f prime of x is going to be equal to, kick it down front, negative 2x to the, now what's the power? Negative 3. Remember, keep getting smaller. Now we reduce that. Now we put it into the denominator. We kind of like re-simplify it. F prime of x is equal to negative 2 over x to the positive third power. The negative 2 stays on top. The only thing being raised to the negative exponent is the x. So that's what shoots down into the denominator and becomes positive. Negative 2 over x to the third. Okay, let's take a look at part B there. So y prime is going to be equal to, actually I shouldn't start with y prime. Let's make that a power on x. What is the third root of x squared as a power on x? X to the what? X to the 2/3, yeah. X to the 2/3 power. Remember, index, if I have nth root of x to the, I don't know, a power, that is always x to the a over n. It's always power divided by index, right? So this is like saying x to the 2/3 power. Remember that the rule still applies. The power rule still applies. 2/3, y prime is going to be equal to 2/3, kick it down front, and then subtract by 1. Okay, 2/3 minus 1. Negative 1/3, right? Negative 1/3. And now we just have to reduce that. Now we just have to take that and reduce it. Okay, negative x to the negative 1/3. So y prime is going to be equal to 2/3 times the negative exponent is going to bring it to the denominator, which is really just saying 2 divided by 3 times x to the 1/3 power. What is x to the 1/3? The third root of x. The third root of x. And I know it seems weird to leave a radical in the denominator, but again, we kind of leave rationalizing the denominator by the wayside here. So 2 over 3 times the third root of x. I can't even begin to describe how difficult this would be using our old formula, the x plus h minus f of x all over h. Ooh, I don't even want to try it. I don't want to do it. It's Friday. Don't want to do it. Okay, let's keep it going, shall we? The power rule enables us to find tangent lines without having to resort to the definition of a derivative, this junky thing. It also enables us to find what's called normal lines a lot easier. Now, you had to find the equation of tangent lines all the time, right? You had to find it a lot on your test. What we're also going to be able to find are called normal lines. Normal line is a curve, the normal line to a curve is the line through that point that is perpendicular to the tangent line, okay? So if I ask you for the normal line, what you have to do is find the slope at that tangent point, then find the perpendicular slope. Remember, perpendicular slope is opposite reciprocal slope, okay? So it just adds another layer that you can use. So find equations of the tangent line and a normal line to the curve y is equal to x square root of x at the point 1, 1. And then we're going to illustrate that by graphing the curve and those lines to see, is it truly perpendicular at that point? Okay, so the first thing is I've got to reduce down y is equal to x radical x. Right? I've got to take this and see if I can create x to the something power. Because if I can do that, then I can find the derivative quite easily. I've never seen it say this down here before. Rain coming. All right, so this is really x to the first power times x to the, what's the power on the square root of x? 1/2. X to the first times x to the 1/2. Well, if I'm multiplying with the bases, don't I add the exponents? Right? So 1.5 is 1.5. So x to the 3/2 power. Right? So that's what we're going to find the derivative of. Y is really essentially just x to the 3/2 power. So let's find y prime. Let's find y prime. So y prime is going to be equal to 3/2 x to the what? 1/2. Which is essentially 3/2 times the square root of x. Right? Because the x to the 1/2 power is essentially just the square root of x. It doesn't go into the negatives because I was above 1. Right? It doesn't go into the denominator because I was above 1 in my exponent. So that's y prime. Y prime is equal to 3/2 radical x. Okay, so it asks me, using the point 1, 1, it didn't really need to give me the y value. We could have found that. But using the point 1, 1, find the tangent line and the normal line. So let's find the tangent line first. Okay, using 1, 1. Okay, what's the slope at 1? Well, I've got to run it through my derivative, right? So my slope is going to be equal to 3/2 the square root of 1. Oh, okay, square root of 1 is 1. So that just ends up being positive 3 over 2. Let's take y minus 1 is equal to 3 halves x minus 1. So y minus 1 is equal to 3 halves x minus 3 halves. Y is equal to, so let's add 1. Ooh, let's make that a weird fraction. Oh, that's not too bad, right? Negative 3 halves plus 1 is negative 1 half. 3 halves x minus 1 half. Negative 1.5, add 1. Yeah, negative 1.5. So that's our tangent line. The normal line would just be taking that slope and taking the opposite reciprocal. M is equal to negative 2/3, right? Positive 3 halves turns into negative 2/3. At that same coordinate, at 1, 1. Okay, so y minus 1 is equal to negative 2/3 x, oops, sorry, parentheses in the wrong spot, x minus 1. Okay, so that means I've got y minus 1 is equal to negative 2/3 x plus 2/3, and then I add 1 to it. Y is equal to negative 2/3 x plus, okay, 2/3 plus 1. So 2/3 plus 3/3 is 5/3. Now the reason I'm using fractions is because I want this to be exact as possible, because I'm going to graph it now. And I don't like the way that the calculator shows it, so I'm going to open up Desmos real quick and use that. Oh, should have just clicked on graphing calculator. Okay, so we want two things. We want the original, which was x radical x. Okay. Somebody knocking. X square root x. You guys know you could type in square root into anything, and it'll, if you just do SQRT, watch, SQRT turns into a square root. Fancy. Okay. And then the tangent and normal line. So 3 halves x minus 1 half. 3 halves x minus 1 half. So 3 halves is 1.5 x minus 0.5. Now, do you see now? Here, look. That's tangent line at 1, 1. And then let's do 2/3 x. Oh, is it negative 2/3 or positive 2? Negative 2/3? Negative 2/3 x minus 5/3 or plus 5/3? Plus 5/3. Yeah? So that's what we did with that algebraically. X radical x is the curve. My tangent line, then my normal line. And it's perpendicular at that point. Perpendicular at that 1, 1. Okay. This is used a lot in, I kind of bypassed it, said it a little bit ago in the notes. This is used a lot when working with like lenses and things like that to find focal points. Because if you can have like a parabolic shape, you can find tangent line, normal line, then you can find the foci of the parabola to see where it'll focus into. Right, that's, you guys got that, right? Yeah. Okay, one last thing here. We'll do one other. New derivatives from old. This basically says that the constant multiple rule, okay? This whole next piece to this is finding, derivatives using the derivatives that we've just learned. Finding more derivatives. Like, for example, if you have a constant times a function, right? A constant times a function, like 7x squared. So 7 being multiplied by x squared. if you have a constant times the function, you can actually take that constant and bring it out front. Why? Because the derivative, because that constant is not, dependent upon that x value. So finding the derivative with respect to x of a constant, you can you can just bring it out front. So c times d over dx of f of x. Okay? So what I'm saying here is that if you have any number out in front of a function, the whole number, not x, whole number, you can bring it out front, find the derivative of the piece that you're looking at, the derivative with respect to x, whatever the function is, then remultiply back that constant back to it. Like for example here, d over dx of 3x to the fourth. What's my constant? 3. Bring it out front. This is essentially saying 3 times d over dx of x to the fourth. Well, what is d over dx of x to the fourth? 4x to the third, right? So this is 3 times 4x to the third. Okay, so 12x to the third. So essentially, you're doing the power rule, but whatever the coefficient was in front of it, you're just going to multiply it back to it. So 3x to the fourth just becomes 12x to the third. Whatever you bring down front, you just got to multiply back to it. Like for example here, if I have negative x, that's like saying negative 1 times d over dx of x. Well, what is d over dx of x? Isn't that our diagonal line? 1. Right? d over dx of x is just 1. So it's negative 1 times 1, or just negative 1. Okay? So if you've got a constant, you can bring it out front and multiply to it. Now, what time is it? 10:47? Let's pick up there tomorrow, shall we? Let's do that. Remind me, I'm at the I guess I'm going to save these notes. Oh, you know what I mean. You know what I mean. Don't. Oh, we will be in new school tomorrow.